It's a pleasure to be here today, and I think that in the course of my presentation you'll hear a lot of repetition of some of the things that previous presenters have mentioned. And the good news about that is that we're all on the same page as we're thinking about how to use the ISS and use it for an analog towards Mars. So I wanted to basically today talk to you a little bit about a technical manual that Dr. John Charles, who's sitting in the front row, his team of subject matter experts at the Johnson Space Center and the Space Life Sciences Directorate put together. They got together and thought through what were some of the things that we would like to see done on the International Space Station that would make it a useful simulation towards going to Mars. This was published, by the way, in February of this year and is available. So just a little refresher on orbital mechanics. We have a couple of different classes of missions that we can think about in going to Mars. The opposition class type mission, where it would be an actual short stay on the surface of Mars, but a very long stay, maybe upwards of 300 days each way in the Earth to Mars and Mars to back to Earth transits. The conjunction class missions, a long stay on the surface of Mars, 545 days or a year and a half roughly, and shorter transit times, maybe 6 months in each direction. And it's certainly, as you look at the differences in communication delays between conjunction and opposition, if we launched here and then 6 months later get to Mars, now we're going to be dealing with about a 7-minute delay in communication. And so it's felt that this is very important to give the reality, that sense of isolation to the crew as they're working through their daily routines. As you look at what we could do with the simulation, of course right now we're operating on 6-month schedules with ISS crews, and so it would be very easy to develop a conjunction class outbound Earth to Mars kind of transit simulation. We could also do simulations that would be longer, maybe in the 9 to 12 month time frame, which would correspond to more of a worst case kind of transit scenario. And then we could also look at missions where it would just be a flyby of Mars and turn around and come back to Earth. And those durations would be about 22 months. So we have experience in 6 months. Our Russian colleagues certainly have experience in 9 to 12 months and a little bit longer kinds of crew exposures to microgravity. But we really don't have any experience in the 22-month time frame. And in these longer missions, although it would reduce the total number of individuals that would fly on the space station, it would certainly give us an opportunity to explore the physiologic and behavioral and psychological aspects of being exposed to microgravity for these longer periods of time. So certainly the team of subject matter experts that John got together felt that indeed it was an opportunity to exploit the ISS to be able to look at both operational and medical experiences and trying to simulate a high autonomy kind of environment for these future missions. They felt that it was important to focus on the Earth to Mars outbound transits of 6 to 9 months in duration. Again, high autonomy of the crew, and it was very important for the reality of the simulation to have an ever-progressive increase in com delay. So as you left the surface of the Earth, the com delay would be minimal, but as you got further along in the simulation of 6 months, now you're starting to see com delays of 7 minutes, roughly. So, actually I didn't skip one here. You've heard many speakers talk about the fact that we have to have really reliable systems and life support, other hardware systems, being able to maintain that hardware on orbit without the reliance of orbital replacement units or the reliance of the shuttle or other space vehicles to resupply this vehicle that is simulating to go to Mars. From a medical standpoint, however, we feel that there are many things to be learned about long-duration exposures to microgravity. And in particular, one of the things that we have had some experience with that needs more evaluation is just what happens to our medications in our medical kits. Will they be effective, a year, 2 years down the road, being exposed to a deeper space environment? And we do have some information that suggests that our medications, not only do they exceed the lifetimes that the medication is certified for, but they actually do indeed show a more rapid reduction in their effectiveness. Same sort of thing goes for food. The way we package food now, and it has a certain lifetime that it can be stored, is not long enough for us to get to Mars and back. So we have to understand, how we can deal with packaging of the food supply and making it palatable and allowing it to make the trip. We also need to demonstrate countermeasures that would be appropriate for going to Mars. So to conclude, we do think that it's certainly possible. Current operations on the space station are certainly amenable to looking at this kind of issue. We do need some long lead times, however, as Pete and our other Mission Operations Directorate members here have alluded to. It takes a long time to plan these missions and get them in place, and for us to design the research that's going to be needed will take quite a bit of time. So, as you're thinking about this, when would an optimal circumstance be? You might look towards more the pre-decommissioning kinds of increments, say last 2, 3, 4 years maybe. But you're really going to need the international partner buy-in to sort of take over the space station, if you will, to look at these kinds of simulation and scenarios. And then, of course, we need to understand what kind of early termination criteria of that simulation would be necessary. For example, what happens if we have a true medical emergency on orbit? Some of the potential issues that we're going to have to overcome, we've already mentioned the ISS as a national laboratory, so there are certain expectations about return on investment that the national laboratory is expected to show. The longer the missions for each crew member means that there are going to be fewer total numbers of crew members fly, and of course that's going to be an issue for international partners who want to see as many of their astronauts and cosmonauts fly. Are there going to be other physiologic issues that we're going to discover? Is bone demineralization going to continue in a straight line, or will it taper off as the crew member gets longer and longer exposures to microgravity? We don't know. Is it going to be an increased risk of kidney stones because of that? Will there be behavioral issues that surface? These are all things that would be very important for us to understand, and again, it emphasizes the need for us to do these kinds of things on the space station. Of course, there are philosophical changes to overcome, in that we've also heard alluded to the ground control philosophy of controlling spaceflight missions versus the autonomy that are going to be required, or that is going to be required to go into deep space. And last but not least, especially as we talk about getting into longer and longer missions and exposures of our crew members to microgravity for 9, 12 months or even longer. Recently we've become aware that some of our crew members, not all, but some, will develop an element of intracranial hypertension and have visual changes. And we need to understand how to select crews, how to medically manage those issues, especially if it becomes more of a problem on orbit. So a lot of research in that area is certainly necessary. So Rich asked me to just make some comments a little bit about our Chilean experience in rescuing with the miners. And certainly there are some parallels in spaceflight which weren't immediately obvious to all of us, but certainly as we went through the scenario with the Chileans, became apparent. So this is the situation, 2,200 feet underground, 33 miners. Initially the reports were that they were trapped in a large living room. That really wasn't the case. They had about 2 kilometers of tunnels that they could work and exercise in. But it was hot, it was humid, and they were certainly isolated. The Chilean ambassador wrote a letter to our administrator, and the Minister of Health provided us a letter with areas of interest that they wanted us to consider from a medical and behavioral health and a psychological support standpoint, but not engineering, interestingly enough. So we met with the Minister of Mining, the Minister of Health. We had the Executive Secretary of the Chilean Space Agency, and then members of my team, Dr. Polk, Dr. Holland, and our engineer, Clint Craig. Every day when we went to the mine site, we were reminded that we had 32 Chilean miners and 1 Bolivian miner, as referenced by this Bolivian flag over here on the side of the mountain. And it was a stark reminder of why we were really there to help these people get through this ordeal. As you might think, we've already landed on Mars, looking at how desolate that is in the Atacama Desert. Unlike these pictures, there were parts of the Atacama Desert that were indeed very beautiful. It had rained there, and so things were kind of in bloom. But this is Camp Hope. The families were staying in these colored tents. This is the mine site where Plan A, Plan B, and Plan C drill operations were going on, and of course it was Plan B that eventually was successful. This is the Plan B rig that arrived the day that we departed. We never had the pleasure of meeting them at the mine site itself. A little known fact is that UPS actually provided the air transport of this rig to Chile at their cost. So we produced a report for our Chilean counterparts that contained information about medical issues, behavioral health support, as well as engineering, design suggestions, and organizational suggestions for their operation down there. The parallels that we saw in spaceflight, certainly this is an isolated, remote, austere environment. There were a lot of stressors involved. They couldn't communicate, obviously. They were isolated for 17 days without any ability to communicate with the surface. They had lack of variety and entertainment, away from family, possible depression issues, as you might well imagine. You know, we see that in stressful circumstances, we get latent virus reactivation. We see that in astronauts that fly in space. Of course, the lack of sunlight, vitamin D deficiencies can arise, hygiene issues. We had a lot of operational psychology and behavioral health issues to deal with. They incorporated the idea of private psychological conferences, which is something that we do in medical operations and dealing with our crews on orbit. Same way with families. We do family support. We have family private conferences where the family can actually talk to the crew member. They did the same with regards to having the families communicate with the miners. Exercise, telemedicine. We actually had what we call a crew medical officer. In spaceflight, we train one of our astronauts to be the crew medical officer. This individual may or may not have any medical background at all. The same way with the miners. They did have one individual that had a little bit of medical training and that he could, give shots, change bandages, having taken care of a sick family member at home. Circadian dysynchrony was a big problem. They were working shifts. They, needed to have, work rest schedules. We needed to try to get them certain light exposures, light, high intensity, the right kind of frequency of light. From the day that they returned to the surface of the Earth, we sort of likened that to entry day of our astronauts returning back from space. So we fluid loaded them because we didn't know how long this ascent was going to take as they were brought up in the rescue capsule. We also had them wear compression stockings, much like the Tauber suit that our Russian colleagues use, or G-suits that we might use on the space shuttle. We were encouraging our Chilean counterparts to work with the families and work towards a reintegration plan for the individual getting back into the family, getting back into society, dealing with the tremendous celebrity that the miners enjoyed once they were rescued. And then, of course, rehabilitation. And the last, I'm a doc here, but I'm also very impressed with the engineering work that our engineering colleagues in NASA were able to provide our Russian colleagues in terms of things to think about in the design effort of this rescue capsule. And of course, it was a tremendous success for the Chilean government and their president. But this is really what it was all about, and that's returning the miners back to their families. So with that, I'll say thank you.